Hey, grade 12s. Hope you had a good weekend. We are going to get back to our electric fields notes. We're going to take a brief pause from doing the problems of the day because some of these lessons that I have here are a little bit longer, and I'd like to dedicate all of the time to trying to get through the content without having to make the lesson too long or split it up into two lessons. So just for the time being, we're going to take a break from the problems of the day. It also makes sense because it's a lot harder for me to make a problem of the day that's related to a specific national holiday of the year when we're discussing electric fields and magnetic fields. Um, if I ever find that I've got a position or an opportunity to do one, we will definitely do it. I'll let you know. But for the time being, we're just going to take a little bit of a break. So we're going to just move on to talking about electric fields for point charges. That's our next set of notes here. There we go. And we'll get started because we got quite a bit to get through today. So today we're discussing electric fields a little bit more in depth than we did in the first couple lessons. Rather than just discussing Coulombs Law, we're still discussing electric fields for point charges, but we're going to introduce a few new formulas today and do a couple trickier, or not maybe not trickier, but a couple of different practice problems. So let's get started. An electric field is the area created by a charge that will produce a force on another charge within it. We show this area and this phenomenon by drawing electric field lines. So field lines are used to represent the electric field around a charge. And remember, there's a couple really important things that we need to remember about field lines. The first is that they show the direction that a positive charge is going to feel a force. So they show the direction a positive charge feels a force. And then the other one is the closer the lines are, the stronger the field. So those are the two really important takeaways from what it's going to look like when we're drawing electric field lines. Let's make this one a strong electric field, and let's make this one a weak one, just to give us a little bit more kind of an idea of what we can do, what our opportunities are. And this one will, I don't know, we won't worry about it for right now. Now, there's three different drawings here that I want you to make. There's a drawing of just that charge up there. There's a drawing of this charge right here, and then there's a drawing of this down here. So I just want to separate. Okay, so let's take a look at the top left. This is a strong electric field around a positive point charge. Now, or a positive test charge. No, hold on, sorry. This is the positive point charge, the positive test charge we would place in it. So anyways, my bad. A strong one would mean that there are more lines than we maybe see in some other examples. Now, one really key thing about the lines is that our drawings don't need to be perfect, but we want to make our lines perpendicular to the surface of the point charge from which they're either leaving or being attracted to. Now, the reason I've drawn so many is because we said it was strong. Now it's positive, and it says it's the direction a positive charge would feel a force. So a random positive charge placed in this electric field would feel a force of repulsion from this positive charge, right? So that tells us that our electric field is pointing away from our test charge, or from our point charge. And then wherever you can, maybe just show yourself, remind yourself that these are all supposed to be perpendicular to the point charge. Okay, so there you have it. That is a strong one. Let's do a weak one here. Well, that just means that we're going to have less electric field lines. There you go. All perpendicular. And in this case, it's negative. So remember, it's the direction that a positive charge feels a force, and a positive charge will feel a force of attraction towards a negative charge. So they're all going to be pointing towards it. And then our last one here is we've got two of them. How do they interact with one another? Well, we would have the positive charge would be attracted to the negative charge, right? If I put a little positive charge here, it would get repelled away from this one and towards this one. That's what we're showing. So then perpendicular from and kind of comes around in a parabolic type shape like that. You could do another one. It would maybe come out and all the way around like this and up here. And then pointing away, and pointing away, and then pointing towards, pointing towards, pointing towards. So that is what it would look like. All right. Remember, like obviously we remember that opposite charges attract one another and equal charges or like charges repel like and unlike. Now, let's review how to calculate the strength of an electric field. So the strength of an electric field can be found by placing a small charged object at some location inside of that electric field. This would be called the test charge. If I was to place one here, maybe I would put it right here. And it's showing us, okay, it's going to feel a force like that, right? It's going to get repelled and then attracted. So that would be our little test charge. So the test charge has to be small enough that it doesn't affect the other charges. So we think that these ones are just stuck in place. And then what would this tiny little charge do? And to calculate the strength of the electric field, we have to use the following formula. E equals F over Q. Reminder that E is the electric field. Let's just write the whole thing out. Lazy. Electric field. And to remind you, we can either measure electric field in newtons per coulomb or in newtons per EC. And then up here, we have electric force. Fe is the electric force. And what is Q again? That's the charge. So, right, newtons per coulomb or EC. That's where this comes from. Okay, so remember, the direction of the electric field is the direction that the force that a positive test charge experiences. So if I was to draw a point charge here, that was positive. And then I was just to place a small little test charge up here. Maybe I placed a charge up here and a charge down here. And let's say that this one was negative, this one had a negative charge, and this one had a positive charge. Which direction would these guys feel a force? So what your job is to do is first off, show me the electric field lines. Show me that the electric field lines go like this, away from a positive point charge, right? We know that. And then, which direction is the force that these feel? Well, if this, sorry, I'm just going to write that this is E. If this is a negative charge, it's going to feel a force of attraction. And if this is a positive force, it's going to feel a force of repulsion. So there you have it. That's how we know this. Remember, from our definition, a positive test charge shows us the direction that the electric field lines are going because it's the direction that it would feel a force. And the negative always feels a force in the opposite direction. So let's move on. Yeah. Let's talk about a new formula. If I want to calculate the strength of an electric field using Coulombs law. So using Coulombs law, well, remember, Coulombs law is F equals KQ1 times Q2 over R squared. And we just learned about the force of the electric force being equal to the charge multiplied by the electric field. I just rearranged it. It was E equals F over Q before. But I think the way that it is in your formula sheet is F equals Q times E. Now, since both of these are equal to the electric force, they can be used to solve for the strength of the electric field. Because what I can do is I can set Fe to be equal to Fe, right? So if I set Fe equals Fe, I mean, that goes without saying, right? But then I just replace the one Fe with KQ1 Q2 over R squared, and I replace the other Fe with Q1 times E. And all of a sudden, I'm getting a cancellation of my Qs, my Q1s, Those are the test charges. Just so you know, these right here, these are the test charges. I'll write it down at the bottom right corner here. But what that ends up giving us then is that E, and we actually have it as a vector. We want to always give the direction of E, the electric field, is equal to K times Q over R squared. Now, in this case, I got rid of the 2 because we're only just concerned with the fact that it's the only charge. And what I want you to say, though, this is the charge that creates the field. This is not, let's write it here, not test charge, not the test charge. We got rid of the test charge. The test charges were the Q1s. This is the charge that creates the field. This is the point charge inside of this formula. Okay? So, let's do an example. At point A, there is a charge of 1.6 microcoulombs. And at point B, which is 60 centimeters to the right of point A, there's a charge of negative 0.4 microcoulombs. What is the strength of the electric field at B caused by charge A? So I'm going to draw this out. I've got charge A right here. Okay, and charge A is positive. I'm going to write it down here. And then I've got a charge B over here to its right. And charge B is negative. And the distance between these two is 60 centimeters. 60 centimeters, which I'm just going to write as 0.6 meters. We'll do that conversion right away. Now, my electric field around A, because A is positive, so my electric field is going away. But that's not to say that the force, what it's asking for, the force of B, which way is it going to be going? Well, B is negative. So there's always going to be an attraction between a positive and a negative. So FE is going to be going to the left. But we see here, if I just continue this, FE is going to the left and E is going to the right. So you've got 2 different directions happening here. That's really important to note, okay? So let's solve for A. What's the strength of the electric field at B caused by charge A? Well, just because B is feeling an attraction doesn't mean that the electric field is also going to be to the left. The electric field is actually to the right. We just showed that. So let's do the example, or let's do the math here. E equals 9 times 10 to the 9, because that's our K value, right? And then our Q value, okay, so which Q do we want to do? We want to do the Q that creates the field, not the test charge. So in this case, A is our Q. It creates the field. So 1.6 microcoulombs. What's micro? Times 10 to the negative 6 is micro. Divided by R squared. And R squared is 0.6 squared. So there you have it. A couple tricky things that you need to remember there, right? It's always the charge that's causing the field, that's creating the field, okay? And then the direction is going to be the way that it's creating that field. So it should be 40,000 newtons per coulomb. And then our direction is to the right. Okay? So there you have it. Let's do part B. Part B, what is the force on the charge at B? So now this is there's a different one now. Now we're looking at the force, and we've already said the force is going to be to the left. So FE at B. So now I use the electric field that I already found, and I use the charge of B, because it's the one that's feeling the force. So Q is 0.4, and it's 0.4 microcoulombs, so I'm going to convert that. 0.4 times 10 to the negative 6 times 40,000 Now, this is kind of, we can't really do vector addition in this sense. We just have to realize by drawing or by thinking that if this is a negative charge and that was a positive charge, then a negative charge is always going to feel a force in the opposite direction of the electric field. So Fe at B is equal to 0.016 newtons to the left. Okay, so there is our little introductory examples. I'm trying to think about how long has my video been here. Let's do this last example. If you don't get to watch it all at the same time, that's totally fine. But I will get it over with, and then you can maybe watch it tomorrow if you have some more time. So, two equal charges, A and B, both of positive 0.6 microcoulombs, are separated by 60 centimeters. Consider a third location, C, that is 60 centimeters from both of the charges as well. What is the net electric field at that location, C? So what we have here is we have equal distances between each of the sides of our triangle. And what that gives us is an easy problem to solve here for the angles. It's just 180 divided by 3. All of the angles, I said 3 and I thought 3, there you go. All of the angles are going to be equal. So there's 3 angles. So that gives us 60 degrees for each of our angles on this problem. Now, A and B are both positive, which means that the electric field at C is going to be that way, right? Away from the positive charges. It's always which way would a positive test charge feel a force? Well, it would feel a force of repulsion. So that's the way that our electric field is going to look at C. Now let's actually just take a second before we get to any math. Let's draw this out and think about this kind of critically here about what is actually going on at C. So this is C, and it's feeling an electric field up to its, northeast and its northwest. Now, whenever I have angles, I always want to change these and separate them into their, oh, I did one dotted line and one not. Okay. Into their X and Y components. Okay, we have an X and a Y component. We have, EX, we can call it, and EX and EY. Now maybe we'll call it EX YB, EXYB, or sorry, EXB, and then EXA and EYA. So that just means that they're coming from these two. These both have the same electric field size, and they're both moving in equal and opposite directions. So what's going to happen right here with these two? What are they going to do? I think you might be able to already guess. They are going to cancel. They are equal and opposite and exactly the same size and just in opposite directions. So they are going to cancel. So what that then means is all that we need to do is find the y components and add them up, right? If we find the y components and we add them up, then we will be just fine. So what I want to do is I actually want to find the electric field due to point B at C and the electric field due to point A at C. So let's find EAC and let's find EBC. But what I think you're going to be able to tell is that EAC and EBC are going to be equal in magnitude. Their directions are just going to be different. So EAC is going to be K times QA. Remember, it's the charge that creates the field over, we'll just call it R squared. All of our distances are just going to be 0.6 meters. So K is 9 times 10 to the 9. QA is 0.6 microcoulombs. So that's 0.6 times 10 to the negative 6 coulombs divided by R, which is 60 centimeters. So R is actually equal to 0.6 meters. So 0.6 meters squared. Now, if I plug that into my calculator, I get 15,000 newtons per coulomb, but I've got a direction associated with it. It's going to be 60 degrees northeast, right? 60 degrees north of east for the one that A is creating right there, right? So that means that EBC is actually just going to be 15,000 newtons per coulomb, 60 degrees north of west. Now, since my X components cancel each other, my total electric field is just going to be EYB plus EYA. So my E net at C is going to be EYB plus EYA. And all that is that I just found 15,000 and 15,000. I just need to do 15,000, and then this is my angle, right? So I need to do 15,000 sine 60 and 15,000 sine 60. So they're actually going to be the exact same thing. 15,000 sine of 60 plus 15,000 sine of 60 should give you, if you plug that into your calculator, you should get 25,980.8. Really, really just don't worry about sig figs for this one because it's going to be way off. So just leave it like this. You can put it in brackets, however many sig figs you should have. Newtons per coulomb, and because our x direction's canceled, our final direction is just north. So E net at C is equal to 25,981 or 980.8 newtons per coulomb north. That's quite a bit of a trickier question. If I were to label like the different steps that you should do, right? You should just do one and then do this and then do this and then put them together here. So those are kind of the steps that you could interchange these, but you would just do an extra equation for no reason. So that is it for today. I know that there's some tricky parts to that, so please do let me know if you have any questions. If you don't know, you can get ahead to working on the practice problems that are associated with this. Good luck with that, and I will talk to you all very soon.